Oh my gosh, there you are. Hey, it's Monday, April 27th, and we're back for some more kitchen table chemistry. And today we're going to take a look at how to write an equilibrium law, which is what we've been working on in this equilibrium unit. Now, next thing we'll do here is take a look at an example. And I think this is the easiest and best way to look at it. So here we've got a reaction. Notice everything in this reaction is a gas. I'm just getting my pencil thing loose here. Okay. So, um, first, everything is a gas. So that means that when we write our K for this, K will be equal to, on the top, the hydrogen iodide, and that will be squared. And on the bottom, the hydrogen times the iodine. Nothing's going to go missing. Everything is in the same phase. Here, we actually have the values given to us, and we're asked to determine the equilibrium constant, and that is the K. So it would like us to find the K for this. So that's where we're going to be. Now, to find that K, what we're going to do is this. Now we're going to go and find the concentrations of these things. So it says the hydrogen iodide here is 0.160. So that means on the top, I'm going to have that concentration, which is 0.160. I'm going to be squaring that. And on the bottom, the concentration of the hydrogen and the iodine, they're both given as 0.200 molarity. So I'm going to have on the bottom here 0.200 times 0.200. I find it's best to parenthesize the whole top and then the whole bottom like that. And I do this, I get K initially, I just did the whole thing in one big swoop here, and I got K equal to 64. There's no units, that's all you get is 64. Now that value does tell us something as well. That tells us that the products are favored because K is a ratio of products over reactants. So with a large K value, this says that the products are favored. And again, if you take a look at our concentrations, much greater concentrations of our products on this thing. All right, questions, answers, there we go. Next, for the reaction below, and again, we inspect the reaction, everything's a gas. We have gas, 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 and gas. So we're not going to be getting rid of anything. We're given K. K is 5.67, and it says the concentration of the carbon monoxide is 0.300. The concentration of the hydrogen is 0.800. The concentration of the methane is 0.400. What is the concentration for the water? Okay, so this is just finding a missing value then. So we'll set this up as K is equal to, on the top, the carbon monoxide times the hydrogen concentration, which will be cubed because of that value. And again, I'm just going to want to put a really weird parentheses on it like that. And then on the bottom, we're going to have this value for the CH4, which we're then going to multiply times the value, square brackets please, for the water. And this is all going to equal K. So 5.67, which is K, is now equal to, I have down here 0.300 times 0.800 cubed over the value of 0.400 times the value for water. So what I then did when I went to solve is I just put water over here. So water, H2O, I had equal to 0.300 times 0.800 cubed divided by 0.400 times 5.67. I just flipped the water and the K value mathematically. That's what I did. And I then got a initial value here of 0.154 on the top. On the bottom, 2.2, and that gave me a final value of 0.0672. molarity, and that is the water concentration. So by doing that, we were able to find the concentration of a missing reactant. And those are the two kind of big ways that we do any calculations with this. And I just gave you a couple of these guys to practice just to get good at it. So it's a very, very short, small practice today for a Monday. And that is, I think, going to be very effective to do, though, because we're going to be going deeper this week. K values. If K is very large, and you heard me say it on the one slide there, K is very, very large. That means that the products are favored. That means most of the concentration is product, and that the products are favored. So if we set this thing up where we've got K is equal to products over reactant, and that is equal to K. If K is large, then it means that we have much more products. What do I mean by large? Like 2 or more. If K is around 1, then products and reactants are about equal, more or less. And if K is small, like 0.00 something like that, that means that the reactants are favored. So we can often tell based on K whether the reaction sits mostly on the product side or on the reactant side, and what that means. X like that. All right. So that's what these values are. And as we go through them, I'm going to keep asking, what does this mean? What does it mean? What does it mean? Because I want you to understand what the K value actually means in the end. All right, kind of like I said, a shortish assignment from Monday. I hope you watched this and it helped you. And take care. Let me know if you've got any questions, concerns, or what have you. All right, guys, over now.